I'm glad to be part of this webinar and thanks for Peruvian Intensive Care Society for inviting me for this lecture. I'm Dr. Fatim Farid Awadallah. I'm a critical care consultant in Case A and Associate Professor of Critical Care at National Heart Institute in Egypt. Today, my lecture is about ECMO Essential and Physiology. In this lecture, I will cover types of ECMO, physiology of ECMO, if it's respiratory or cardiac, and quick review of circuit design. ECMO means extracorporeal membrane oxygenation, and the circuit of the ECMO is a closed circuit where the blood comes out from the patient and the same blood returns back to the patient. Not like a bypass machine where there is a reservoir, some of the blood will return. And when it comes, the blood comes taken or aspirated by the pump, which will act as the heart of the circuit, pushing it to the oxygenator, which acts as the lung of the circuit, then return back to in the return limb to the return cannula. And during this process, there is a sweep gas which added in the oxygenator, allowing gas exchange inside the oxygenator, the same like what happened in the lung. Two types of ECMO, VV ECMO or respiratory ECMO, where it bypasses the lung, used as a support to the patient with respiratory failure. It requires a good native heart to pump the blood into pulmonary and systemic circulation. The second type is VA, veno-arterial ECMO or cardiac ECMO, where it is bypass the heart and the lung and can use to support a patient with cardiac failure with or without respiratory failure. The first part of our lecture is the physiology of ECMO, whatever it's veno-venous or veno-arterial ECMO. Physiology of ECMO. BCO2 or CO2 clearance is under control of gas flow. If we have we wanted to increase CO2, CO2 clearance, we can increase the gas flow. BO2 is under control of the blood flow. We have low BO2, so we can increase the blood flow. Also, the patient can affecting by the patient temperature will be affected. So we can use heat exchanger, which initially will affect the metabolic rate, and then this metabolic rate will have affecting mixed venous saturation, and finally also the arterial BO2. And what type of veno-venous or veno-arterial? These three principles of any type of ECMO will go. Respiratory ECMO, why it is needed? ECMO physiology. The question is, we know, I think we all of us agree that CO2 removal and oxygenation is the rule of ECMO. But did veno-venous ECMO support the hemodynamics? Did the patient who has a veno-venous ECMO will have support or enhanced hemodynamics? This is important question should be answered. Regarding hemodynamics, the rationale is there is no direct hemodynamic impact for VV ECMO as the blood return exactly matching the drainage. So there is no risk of overloading the RV. Systemic blood flow is equal to native cardiac output, so there is no contribution of ECMO blood flow. The question jumping to the mind, why there is some improvement in hemodynamics while we are using VV ECMO? There is indirect hemodynamic support, and after inserting ECMO, we will decrease ventilatory support or ventilatory pressures. So the patient who have ARDS and require ECMO, he has high ventilatory pressure like high plateau, high PEEP, and high tidal. So at that time, we decrease all of these, put the patient on a lung protective strategy, and that will help to decrease positive intrathoracic pressure and increase venous return.
Also, there is decrease in right ventricular afterload, and that will happen because of relieving of pulmonary vasoconstriction. Improving cardiac contractility, and that will happen when we're correcting the hypoxemia, and removing CO2 and correction of acidosis.
Second function of AV ECMO is CO2 removal, and this function is sweep gas flow rate, which equal to native alveolar lung ventilation, and the rate of CO2 removal determined by the sweep gas flow rate. We use lower rate of sweep gas that lead to build up of CO2 as it diffuses across the membrane, so that will lower the gradient and less CO2 diffusion out of the blood, and the opposite is true when you used a higher rate. The summary of CO2 removal during VAV ECMO: lower sweep gas will give higher BCO2. Higher sweep gas flow rate will lower BCO2. Clearance: CO2 is more soluble and diffusible in the blood than oxygen. So CO2 is not clearance, is not a difficult issue. CO2 the only concern, so much lower blood flow is used. Also, hemoglobin not an important issue in CO2 clearance. The only condition where CO2 clearance is less than oxygenation due to effect of water accumulation on gas side of the lung membrane. That's why if we use low sweep gas, we should do at least 3 times per day ventilator sneezing by increasing the sweep gas to 10 to 15 liters per minute for 10 seconds, to washing the water from the oxygenator side, then we return back to our sweep gas used. If we have only hypercarbia for the patient, so and low sweep gas, every 8 hours we should do oxygenator coughing, sneezing, whatever the name, and this is done in 10 seconds. We will increase the sweep gas to 10 to 15 towards the water from the condensed water from the membrane side.
The most important part for oxygenation is to maintain aerobic metabolism. Oxygen content is referred to the amount of oxygen in the blood. And if we go for arterial oxygen content, it's equal to the amount of oxygen bounded to hemoglobin plus the oxygen dissolved in the plasma. For oxygen bounded in the hemoglobin, it can be increased oxygen content by increasing hemoglobin concentration. And if we speak about oxygen dissolved in the plasma, we will find that this can be neglected as it's 0.003 multiplying in PO2. So it's neglected and not important in oxygen content. If we go for venous oxygen content or oxygen in venous blood, it's the same equation, but the difference is we use SVO2, and instead dissolved oxygen in the plasma will be BVO2 in the venous side, and also the dissolved oxygen in the plasma will be neglected. So if we need to increase oxygenation on the ECMO, one of its parameters to increase hemoglobin concentration.
About oxygenation, we need to define some terms. Oxygen delivery is the amount of oxygen delivered to the tissue, and it is equal to cardiac output multiplied in arterial oxygen content. For VV ECMO, we can increase arterial oxygen content, but in VA ECMO, both of them, cardiac output and arterial oxygen content, can be increased. The second term is oxygen consumption, and it is amount of oxygen uptake by the tissue, and it is equal to amount of cardiac output multiplied by the difference between arterial oxygen content minus venous oxygen content. And for oxygen consumption, there is a relation will be described later on.
If we coming for cardiac ECMO, so why is needed? The most important indication for cardiac ECMO is hemodynamic support. And that coming from where? We have ECMO flow, which distal to aorta, plus the native cardiac output, which is delivered to aortic arch. In peripheral VA ECMO, we will have two flow admixing in the aorta, and their mixing depending on the ratio of native cardiac output and ECMO flow. Usually, the ratio will be 20% of the native to 80% of ECMO flow. What is a hemodynamic target from VA ECMO? First, ventricular decompression to prevent myocardial ischemia due to decreased coronary perfusion, facilitate myocardial rest and recovery. Ensuring forward flow through the heart, preventing LV distension, LV thrombus, and pulmonary edema. Achieving ideal MAP, mean arterial blood pressure, that balances tissue perfusion with afterload reduction.
The mean hemodynamic target for VA ECMO is to achieve right ventricular decompression and prevent left ventricular distension. That will happen by ECMO, which drain blood from right atrium, so that will lead to decrease right ventricular preload, lead to the right ventricular decompression. Right ventricular decompression will lead to decrease left ventricular preload, and that will achieve small amount of left ventricular decompression. But in peripheral VA ECMO, the blood will return back into aorta, and that will increase left ventricle afterload, lead to increased left ventricular distension, and pulmonary edema will happen. Persistent drainage of Sebacean vein and bronchial veins into left atrium, not drained by ECMO, so LV distension will be happened.
Then we will come to the second part of the lecture, ECMO circuit component. To describe the ECMO circuit, we will not have difference from VV or VA except in the cannulation. If we come for VV ECMO, the cannula, drainage cannula, will be from femoral vein, and it will go to the pump, and from the pump to the oxygenator. The oxygenator itself is connected to heat cooler or heat exchanger to warming the blood. Then the blood from the oxygenator return back to femoral vein, and this is the return cannula will be in the vein. But in VA ECMO, the drainage cannula will come out from the femoral vein, and from the femoral vein to the pump, and from the pump to the oxygenator, and the oxygenator is also connected to heat exchange, and from the oxygenator the blood will return back through paternal cannula, but at that time it is to femoral artery. We should note that the name of the ECMO, VV. The first letter is the drainage. The second letter is the return. So if I said VV, so the drainage is vein, and the return is vein. If I said VA ECMO, the drainage is vein and the return is artery. ECMO circuit component started by the cannula, drainage and return, pump, which you have console, pump head and driver, oxygenator, heat exchanger, gas blender, flow meter, and pressure monitoring. First, the principle of ECMO circuit design should be suitable for long-term support, biocompatible, small surface, minimal blood surface interaction, it's easily portable, small priming volume, high oxygen and CO2 exchange, easily adaptable to a wide group. The most important part in the circuit is the cannula. And first we have drainage cannulas, which is transfer the blood from the patient to the circuit. And whatever the type of ECMO, drainage cannula, always venous cannula. It is usually will be long, multi-stage cannula with multiple pools along the length. Multiple pools, and it's wired reinforced to avoid kinking during or collapsing during negative suction of the pump. The second type is return cannulas. Return cannulas can be in venous side or the arterial side. In veno-venous, it will be venous, and in the arterial side will be VA and VA. And it's characterized by short, single cannulas with one hole at the tip. Sometimes there will be your connections, which when we use in veno-arterial or VA ECMO. So at this pore, we will connect to distal perfusion cannula to perfuse the limb during VA ECMO. Important thing for the cannula to determine if it's drainage or return function is the length of the cannula. Short cannulas can be used as a return for internal jugular vein and FemJag configuration, VV configuration, or in femoral artery in FEM-VA configuration. But if we will use a long stage single stage return cannula, can be used for femoral vein return and FEM-VV configuration. Modern cannulas are thin-walled, flexible, kink resist. They are wired reinforced to resist collapse under negative pressure or rupture under positive pressure, but they can trigger inflammatory and clotting response. Coating like heparin can be used to improve biocompatibility and reduce thrombosis. The pump in the ECMO means the heart. It's pumping the blood. So it will create the negative pressure in the circuit and generate force to drive blood from the patient. Then push the blood to the oxygenator, then to the return cannula of the patient. Which type of pump, ruler or centrifuge? It's most commonly to use centrifugal pump in the ICU, but this depends on local experience, availability, and economics. Usually, a ruler pump is more cheaper than the centrifugal pump, and it's used in bypass machine. It's afterload independent, and that means the pump will push the blood even the patient is severely hypertension, so no flow meter is required, and that will increase blood trauma and tubes debris. No backflow occur. It's cheaper, short-term use, bulky. Circuit disruption can occur from excessive line pressure. If we have high blood pressure and we use VA ECMO and we use ruler pump, so sometimes will happen circuit disruption, greater risk of air embolism and less priming volume. For centrifugal pump, it is afterload dependent, so at that time we need flow meter, decreased blood trauma and tubing debris. Also, retrograde flow is possible if the pump stopped. It's inexpensive, can use for long term, it's portable, no circuit disruption, and less risk of air embolism and require more priming volume. And this photo, this is two types of ECMO console. The first one have the monitor in the front, and the other the monitor is up. And here is the knob for changing the speed, and the speed is fixed, done by the operator, and the flow is changeable. If this pump is centrifugal pump, it's preload sensitive and afterload dependent, so it's changed from time to time depending on the patient. And it's very important to monitor the speed and to trace it over hours with the flow to avoid unnecessary drop of the flow while we monitoring the patient. Come to the most important part in the circuit, which is oxygenator. And the oxygenator, the first important thing is the connection to sweep gas or oxygen source or gas blender wall. This is very most important thing. If not connected, this is gas failure and lead to hypoxia. And from here is the blood from the pump entering to the oxygenator, where the oxygenator acting as a lung and the alveoli of the lung, so the blood will come out through this blood going to return cannula. And From down, there is connected to heat exchanger. So there is heat exchanger have water vapor will warming this blood inside the oxygenator to avoid cold blood to enter to the patient and causing hypothermia. Practice, we have two types of hollow fibers of oxygenator, polypropylene and polymethylbenzene. Polypropylene was old, very rare to be used in modern machines, but maybe in some low economic countries still used, as it's a short-term use, very cheap. It's a hollow fiber, have micro tears where is gas exchange occur. There is protein leaking, wetting, avoid the lipid. And that's why we should know the type of oxygenator, because if the type we used polypropylene, so the patient shouldn't be sedated with propofol. But if we have polymethylbenzene, it's long term, the closed fiber microscopic lined by a membrane, and don't wait over the time, low resistance to flow. And here we can use very simple propofol, no issue in that. So it's very important when you have a new machine to check the type of oxygenator in it. Another important part in the circuit is the oxygenator part, or the type of delivered oxygen, FDO2. We mentioned it FDO2 to differentiate it from FiO2 from the monitor. And from here we can increase the oxygen. And here the sweep gas. This is the adult part and this is the pediatric part. And from here we can increase the sweep gas to wash CO2. Part in the ECMO circuit is hand crank. And this is hand crank should be present in the circuit as a backup if we have pump failure or problem in the pump. So we will power failure in the machine. So we will take the pump out and insert the pump like this picture inside this hand crank and start to use the hand crank. The changer, it is a very important part in the ECMO circuit, which is either separated in the ECMO circuit before the oxygenator or integrated in within the oxygenator. Non-sterile water of the heater device separated from the blood by stainless steel or polyurethane. These areas are well glued to avoid contact between the blood and the water, like external water bath. The device utilizes the concept of counter-current flow, so the blood and water will flow in the opposite direction and warming to the blood. Changer, why needed? The blood circulates in the extracorporeal system. Multiple blood transfusion can be present. Ambient air, sweep gas, all of these need to warming the blood. If there is fever, or decrease oxygen consumption or neuroprotection, it's very important to control the ECMO temperature by heat exchanger. Used in ECMO circuit are polyvinyl chloride, and they are biocompatible surface and always connected together and strictly tied together to avoid any disconnection or dislodge. Another important part of the circuit is SVO2, or pre-oxygenator sensor of the ECMO circuit. It's an optical sensor. This is the optics, and the connection it's put on the connecting for the venous probe sensor cable, and they put on the entry of the blood into the oxygenator. Important thing in the ECMO circuit is a flow meter, which is put on the venous lamp on the same direction of the blood flow. Why flow meter is very important? So it's the centrifugal pump, as we mentioned, is preload dependent, afterload sensitive. So the flow correlated with the circuit and the cannula size. For given RPM or speed, any increase post-pump resistance will cause decrease in the flow, like kinking, clot, or increase mean arterial blood pressure in VA. Important part for flow meter, it's bubble detector. Ultrasonic can detect the bubble in the circuit. If there is no air, the current will go from direction to another direction. In case sense a change from normal blood flow and trigger alarm automatically to stop the flow. Here there is air, so the alarm is triggered and the flow is stopped. Bubble detector can be put on arterial or venous lamp or both of them. In this video, this is a console for pediatric from pediatric child. There is some air, so the flow started to decrease, and this is alarm that the flow is decreasing to manage the air and correct the condition before restoring the flow. Another important part of the ECMO circuit is the pressure inside the circuit. For the first one, which is before the pump, pre-pump or P1, and the negative pressure. This is negative zone, or we mention it non-touching zone. Any touch or dealing with this zone or opening or connection will lead to air embolism inside the circuit. And the second one is pre-oxygenator, B2 or positive pressure, and this is post-pump pre-oxygenator or positive pressure. The third one is B3, which is positive pressure also, and is post-oxygenator. And it's very important to know the values of these pressures and monitoring them to detect any problem inside the circuit. To summarize, the data appear on the console monitor. For this is RPM or the speed, which adjusts the flow liters per minute. And in this is the range pressure, P1 or P1, which is minus, and usually ranging from minus 50 to minus 100. And this is post-pump pre-oxygenator pressure, and it is from the highest pressure in the circuit. And delta pressure is the pressure across the oxygenator, which is difference between P2 minus P3, and it's very important to indicate membrane function. And P arterial or P3 or return pressure, which is post-oxygenator pressure. And here the temperature of the blood inside the circuit, and SVO2 is mixed venous saturation of the circuit, which is measuring the blood entering into saturation entering into the circuit. We need more lectures to describe more in the circuit monitoring and details of the circuit part. I wish I summarize it as I can.
These are references of this lecture. I also depend on ELSO Red Book.
Thank you for this invitation. I tried to summarize the physiology and the essential part of the circuit very quickly. I hope you get my point, and if you have any questions, I'm ready, and I'm ready for more lectures if you like.